Hello, my name is Abdurrahman. I'm presenting this on behalf of myself, Kishan Yan, and Zilin Liang. Our goal in this presentation is to demonstrate the application of the Six Sigma method in order to improve a toy car assembly line. Here is the list of our tasks for this assembly line, which includes setting the frame, installing the car seats, installing the car doors, installing the steering wheel, mounting the tires, installing the 4 batteries, fixing the headlights, fixing the car roof, tightening the tire screws, covering the battery door, adding the car windows, and packaging the final product. This is the order in which the tasks must be completed. So the way to interpret this is you cannot install the car seats unless you set the frame. You cannot fix the car roof unless you install the car seats, install the car doors, and install the steering wheel. And you cannot obviously package the final product until you finish everything else. So this is our matrix where we combine the preliminary steps for each task. We combine the times for the preliminary steps for each task and associate a weight. And we rank the weight in order by the highest all the way down to the lowest. This is a positional weight heuristic method. This is a heuristic method called the positional weight heuristic. And through this heuristic, we have generated a new sequence of tasks in which we can start combining them into workstations. So the next step is to calculate the lower bound using the cycle time of 28.8 seconds and the sum of standard time. So our calculation gives us a minimum of 3 workstations for this assembly line. The problem that we run into is that we cannot exceed the minimum number of workstations. So we cannot have an optimal solution more than this because of a very large task time for task I, which is station 3. This task time cannot be broken down since only one task is involved in this workstation. So the question now is, what can we do to bypass this problem and allow ourselves more room for optimal solutions? We want to use a method called Six Sigma. Six Sigma is a set of techniques and tools used for process quality and management improvement. This method was developed by Motorola in 1986, and it is now the most popular management methodology in the history of mankind. The reason why it's called Six Sigma is that its success is measured using standard deviations. The success is measured in the lowest number of defects per volume of outputs. So an easier way to interpret this is sigma level 1 is 690,000 defects per minute. So that would be a very large standard deviation, and this would be included in a process where defects are expected, such as a refinery process. Sigma level 6 would be 3.4 defects per million, and this would be something like a mail sortation plan where you cannot afford any defects, or you can not afford more than the lowest possible amount of defects because you can't have a package going to the wrong address, for example. So those are the methods for measuring the success of Six Sigma, but what about implementing Six Sigma? Well, there's 2 methods for that. One of them is called the DMA-DV method, and one of them is called, and this is for designing a new process, and the other is called the DMAIC method for improving a current process. This is the one that we will use in this assembly line. So the DMAIC cycle is Define, measure, analyze, improve, and control. So first we define the goal, by which we already did, and we mentioned that we want to increase our range of possible optimal solutions by having the ability to include more workstations. We want to measure the process to assess the current performance. So we have 3 stations with 3 workers. We have the time for station 1, which is 25 seconds, station 2, 24 seconds, station 3, 23 seconds. The average for these times is 24.6 seconds per unit. The maximum production is 5,760 units per week. The cost of this strategy is $1,350 per week, or 25 cents per item. The idle time is the maximum idle time is 12.4 seconds. The next step is to analyze the process in order to identify the main causes of our variations. We know that we have a minimum number of 3 workstations. We cannot exceed this number due to a large task time of 24 seconds for task I. We need to find a way to lower this task time so that we can have more than 3 workstations. This is our main cause of our problem. So the main step in the DMAIC method is to improve the process. So we generate multiple solutions in this process. Our first solution is to divide task I into 2 parts. So once we divide task I into task I part 1, task I part 2, we can implement a solution containing 5 workstations. So this is our layout for 5 workstations. We add a buffer in between after station 2, and you can see that station 3 has task I part 1, station 4 has task I part 2. The idle time in between is 2 seconds, and then we have station 5, which is 15 seconds. Our next solution is 7 workstations. So again, we use station I part 1, station I part 2, but in this solution we use GJ for station 4, and we add a buffer in between station 3 and 4. And we use L for station 7. 7 stations has more idle time, so this is not better than having 5 stations. So let us attempt to include 1 more workstation. So here's our solution for 9 workstations. In this solution we have 2 buffers. Our total idle time is 5 seconds. We divided task I into 3 parts. If we use this strategy, the number of defects are also decreased because we would have more workers to work on this process. The quality of the production using this method is also improved, which is a bonus. So if we were to use this strategy, we calculate our results in our performance. So this would be 3,508 units per day, or 17,544 units per week, which is a huge improvement in production. However, the cost is also increased at $6,050 per week. This is because we have more workers and the addition of buffers. This strategy can be implemented depending on the plant's budget constraints and customer demand. If a high demand would be required, this improvement strategy may be feasible if it meets the budget of the plant. Otherwise, if a high demand is not required, we can revert to the old strategy. And this is the way that we control this solution. We apply this solution in the future. And our source for this presentation is on the screen, as you can see. Thank you for watching.